I'll be honest with you. Originally, I wanted to start this video by telling you the story about light guns, technology behind it, technical difficulties and blah blah blah, but then I decided to cut the crap and get straight to the point. And the point is that I modified this Nerf gun so you can play Doom with it. Let me show you. So this is how it works. You can control the camera by moving left or right naturally, simple as that. You can move forward, backwards, strafe left or right by pulling the stick on the bottom. You can press the stick to activate switches, open doors, etc. You can also press and hold the stick to freeze the camera, which allows you to recalibrate the position of the gun with the position of the camera. And of course, last but not least, you can pull the trigger to shoot demons, because that's what Doom is all about, right? So let's see if I can finish this level, complete this level on ultra violence using our Nerf gun. Okay, we have a zombie on the left, zombie on the right. Easy, no problem. Let's open the door. Went smoothly. It doesn't always work like that, to be honest. Okay. Ooh. No. Tried to align them, but that didn't work. No problem. This is a simple one. Yeah, the biggest problem in Doom are the zombies with the shotguns. They are nasty. That imp almost got me. It's close. Open the door by clicking the stick and that barrel. Shoot that barrel. Done. Okay, we're practically done. One imp left. Let's get him right on the button. And that's it. We completed the first level by using our Nerf gun. So now let's see how this thing actually works. This is how a controller looks inside. Obviously, I had to remove most of mechanical parts to get some space for our components. Behind this wired mess, you might notice 5 components which constitute our system. This one is MPU 6050 gyroscope plus accelerometer, which gives us rotational velocity around all 3 axes. It's connected to our Arduino board via 4 wires: power, ground, serial clock and serial data. I understand that it's hard to see anything in here, so don't worry, all schematics can be found in the description of this video. Here we have a simple button, which gets pressed by pulling the trigger, like this, with the help of this piece of plastic which acts as a spring. Here we have a KY023 joystick module, which provides us with a value of displacement along Y and X axis, and also acts as a button, which is very useful. This is a piece of prototyping board which I soldered myself, and it provides what I call a bus, even though technically it's not. One bus for 5 volts and one bus for 0 volts, and also it puts 10 kilo ohm resistor between button and Arduino so that we don't short circuit our board on every button press. And lastly, in the center we have our Arduino Nano Every, which orchestrates all the components, makes some trivial computation and sends the data down this wire to the computer via serial interface. Code for Arduino part is fairly simple. We use Adafruit library to do the heavy lifting regarding setting up and getting readings from our MPU 6050 module, and we simply start filling our data packet with information. First 2 bytes are reserved for a header, which is a way of telling the receiver where our packet actually starts. Next goes rotation velocity around z-axis, converted from radians to degrees for efficiency. Then we send trigger button state, joystick position along X and Y axis, and lastly state of the joystick button. After that, we send all that data via serial port to our computer and wait for 29 milliseconds. You probably wonder why 29 milliseconds exactly. The thing is, Chocolate Doom runs at a rate of 35 frames per second, meaning one game tick equals roughly 29 milliseconds. Any data that comes in between those ticks will be bufferized or lost, which is not what we want, so 29 is the minimum value we can safely put here. On the game side, it's not much more complicated either. Our journey starts in d_loop.c file, where we added 3 functions. Serial open is quite straightforward. It reads command line serial path parameter, which is the one corresponding to our Arduino device. It's going to look something like this. You can find the exact value by opening Arduino IDE and checking the bottom right corner. After that, it simply tries to open the serial port at the provided path, and in case of success, stores the corresponding file descriptor in a global variable. Not gonna lie, try_open_serial function was mostly generated by my friend Claude. However, there are a couple of things worth your attention. First of all, it's baud rate set over here. These values should match the baud rate set on the Arduino side, otherwise the data transmission will become misaligned, resulting in corrupted data. And second, these two values control how reads from the serial port are made. In our case, we do what's called a pure timed read, meaning we read whatever in the system's buffer, and in case there is no data at all, wait for 100 milliseconds and continue the execution of the program. Lastly, we clean up after ourselves by closing the serial port in case game is closed for whatever reason. In build new tick function, we simply pass the serial port file descriptor to the build tick cmd function where all the magic happens. It brings us to serial read function, which does all the heavy lifting. First of all, we read whatever there is in the system's buffer into our local buffer. But why the local buffer even needed? The thing is, we send our data from Arduino in the form of 12-byte packets. However, those 12 bytes don't always arrive at the same time. It means that upon reading from a serial buffer, there can be up to 12 bytes of data. So for example, if it turns out that there is only 5 bytes to read from the system's buffer, we still need to wait for the rest 7 bytes to arrive. However, we don't want to hold the execution of our program, so we put those 5 bytes into the local buffer and proceed with the execution. Then we search for so-called packet header to find where the packet starts, and if we found one, read 10 bytes next to it and parse the data. In order to pass rotation velocity, we need to perform some unit conversion. The thing is, Arduino sends us rotation velocity in degrees per second. However, Doom scene updates 35 times per second. So we need to account for that by dividing what we received from Arduino by the value of tick rate, or 35 in my case. 10,080 is honestly just a magic number I found by trial and error, and you can think of it as a sensitivity parameter. Rest of the data is read more or less as is. We check whether joystick button is pressed and treat it as a use action, which is bound to spacebar by default. And also we store time steps of the last 3 joystick button presses to implement the double and triple click functionality. If joystick button hasn't been pressed in the last 2 ticks, we unblock the camera and apply the rotation velocity to it. If 2 clicks did happen within 5 to 15 ticks, we treat it as a double click and select the next weapon. Moving calculation is quite straightforward as well. We simply normalize the joystick displacement values and multiply it by scale factor of 30, which is again just a magic number I found via trial and error. If trigger button is pressed, we activate the attack and deactivate it otherwise, nothing surprising over here. And lastly, we move rest of unprocessed data in our local buffer to the start, so that we use our memory efficiently. And I believe that's about it. Now you know how to build your own input device for playing Doom, or probably any other open source game of that kind. On that note, I want to thank you for your time and wish you happy dooming. Bye bye.